Here we're going to look at a nice problem from the 2019 Macedonian Math Olympiad. So this is question 4, and it's a mixture of a question involving a functional equation or a functional relationship and some number theory tactics. So our goal is to find all functions from the natural numbers to the natural numbers such that we have this divisibility condition. So n factorial plus f of m factorial divides f of n factorial plus f of m factorial. So notice here the factorials are outside of the function, but in this last instance, they are inside the function. And here I want to point out that I'm using natural numbers to mean 1, 2, 3, 4, and so on and so forth. So in other words, positive integers. Okay, so maybe the main hints on functional equation or functional relationship type problems are to look at special cases, like maybe n equals 1 and m equals 1, n equals 1 and m is free, so on and so forth. But apart from those basic hints, which really work for all problems involving functional equations, I've got these 3 following hints for this problem specifically. So I first want to recall this very basic elementary rule involving divisibility. First, it's the definition. So A divides B if there exists an integer k such that B equals A times k. In other words, B is a multiple of k. So the sentence A divides B and B is a multiple of A, those are synonyms. Okay, and then another simple result from that is that if A divides B and A divides C, then A divides B plus or minus C. And in fact, it divides something like bx plus cy for any integers x and y as well. My next hint is Wilson's theorem, and that is if p is prime, then p minus 1 factorial is congruent to minus 1 mod p. So I think there's a pretty big hint that we should be using Wilson's theorem here, because first off, we've got divisibility. Whenever we've got divisibility, we probably want to work with prime numbers one way or another. And then also we've got factorials. And then whenever we're working with factorials and prime numbers, Wilson's theorem is kind of an obvious thing to work with. Next thing that I want to say as a hint is this fact. And that is if something is divisible by infinitely many numbers, that something is equal to 0. And now here's a little proof of that fact. So let's suppose we've got a non-zero number. So any non-zero number can be written as a product of primes. So here I have p1 to the r1 plus all the way up to pk to the rk, where those pi's are distinct primes, and these ri's are just the powers that are required there by the fundamental theorem of arithmetic. Then we can easily use a counting argument to say that this capital N has R1 plus 1 factorial times R2 plus 1 factorial, all the way up to RK plus 1 factorial divisors. But that number is most definitely less than infinity. So if we've got a number that's non-zero, then it has finitely many divisors. But then it's pretty easy to show that 0 has infinitely many divisors. In fact, any non-zero number divides 0. Just let's talk our way through that. Notice that A divides 0 because we can write 0 as A times 0. So that's good. Okay, so maybe give this problem a go with these hints and we'll come back with a solution. So hopefully those hints were helpful. Now we're ready to launch into a solution. So we're going to start with maybe the simplest setup, and that is m equals n equals 1. So let's do that. So let's set m equal to n equal to 1 to see if we can use whatever this condition is with those values to get some value for the function. So notice our defining condition over here now becomes 1 factorial, which is 1, plus f of 1 factorial divides f of 1 factorial plus f of 1 factorial, but 1 factorial is 1. So that is our defining condition with m and n equals 1. But then also, we know the following fact, and that is 1 plus f of 1 factorial divides itself. So let's go ahead and write that down. 1 plus f of 1 factorial divides 1 plus f of 1 factorial. So now let's see what we've got. We've got 1 plus f of 1 factorial divides this thing which I'm underlining in orange, and it divides itself, which is this thing that I'm underlining in purple. But that means that it will divide the difference of those so long as the difference of those is not equal to 0. If the difference of those is equal to 0, well, there's no real good notion for a number dividing 0, so the argument kind of disappears or doesn't work there. So let's go ahead and point that out. So I'll write orange minus purple is not equal to 0, but notice that orange minus purple is f of 1 minus 1 not equal to 0, but that's equivalent to saying that f of 1 is not equal to 1. Then we have 1 plus f of 1 factorial must divide orange minus purple. But dividing orange minus purple means that we're dividing f of 1 minus 1. But then a divisibility relationship has built inside of it an inequality. So if one number divides another, and we know that they're both natural numbers, then that means that we have this number is smaller than or equal to this number. So we can write 1 plus f of 1 factorial is less than or equal to f of 1 minus 1, like that. Okay, great. So now we're going to work this inequality towards the other direction. So let's notice that also we know that f of 1 is less than or equal to f of 1 factorial. But now we can mold this thing so that the sides of it look like the sides of that inequality up there. So I'll subtract 1 from this side. I'll add 1 to the right-hand side. That's going to change this not strict inequality to a strict inequality. So we've got f of 1 minus 1 is strictly less than f of 1 factorial plus 1. But now notice that these two things that I'm underlining in blue are inconsistent with each other. So we can really hone in on that by extending this inequality with the first inequality that we found to see that this is less than or equal to f of 1 minus 1. So now looking at the extreme left and right hand side of this inequality, we see f of 1 minus 1 is strictly less than f of 1 minus 1. But those are clearly equal to each other, so that gives us a contradiction. So what did we contradict? Well, we contradicted this assumption that fueled all of these arguments, and that assumption was that f of 1 is not equal to 1. So in other words, we know that f of 1 is equal to 1. So we have our first value of our function. Okay, great. So let's go ahead and clean this up. We'll take that tool and keep going. So we worked through this first special case when m and n were both equal to 1, and we got the fact that f of 1 was equal to 1. Now we're going to play two games. We're going to set m equal to 1 and n be free, and then m equal 1 and n be something that's not quite free. So let's go ahead and do that. We'll have m is 1, and then n equals n. That's what I'll write, and I just mean that it's like free to be really any natural number. So let's go ahead and see what our divisibility relationship is in this case. So we're going to have n factorial plus f of 1 factorial, but we know f of 1 is 1. So that tells us that we have n factorial plus 1 divides. Now over here we have f of n factorial plus f of 1. But again, we know f of 1 is 1. So we know f of n factorial plus 1 is the other side of this divisibility thing. Great. But now, again, like we did before, divisibility implies some sort of inequality. So this is going to imply the inequality n factorial plus 1 is less than or equal to f of n factorial plus 1. But then we can subtract 1 from both sides. and then maybe also get rid of the factorials on both sides, because that will maintain the same inequality. And that leaves us at this point right here, n is less than or equal to f of n. And this is true for all natural numbers n. We know it's true for all natural numbers n because we started up here with n being like free. Okay, so now we're gonna do the same thing again, but n is not going to be free. It's gonna have some structure to it. And here we're gonna be motivated by Wilson's theorem because we see factorials here. So let's go ahead and look at that case. So we've got m is 1, and then we have n equals p minus 1, where p is any prime. And it's important that it's any prime in this case. Okay, so let's see what our divisibility condition ends up looking like in this case. So we'll have p minus 1 factorial plus 1. So that's the left-hand part of this. Divides, so it's going to be f of p minus 1 factorial. So f of p minus 1 factorial plus f of 1, but that's just 1. Okay, good. But now let's use the definition of divisibility to simplify this a little bit, or to write this in another way. So that tells us that f of p minus 1 factorial plus 1 is a multiple of this stuff over here. So I'll just say that it's k times p minus 1 factorial plus 1. Now we're going to go ahead and reduce this modulo p. So notice modulo p, this is going to be k times negative 1 plus 1, again from Wilson's theorem, because p minus 1 factorial is minus 1 mod p. So this whole thing is 0 mod p. But notice this implies that f of p minus 1 factorial is congruent to negative 1 mod p. And that actually gives us some sort of hidden inequality. And let's see what that is. So let's notice that if f of p minus 1 is bigger than or equal to p, then p factorial divides f of p minus 1 factorial. So just think about it. If you've got 7 is bigger than or equal to 5, well, 5 factorial is going to divide 7 factorial, because 7 factorial is 7 times 6 times 5 factorial. So anytime you've got an inequality like that, you factorial it, you get this nice divisibility relationship. But now, since p is a prime and p factorial divides f of p minus 1 factorial, that tells us that p divides f of p minus 1 factorial. In other words, f of p minus 1 factorial is congruent to 0 mod p. So let's see what we've got over here. Here we've got f of p minus 1 factorial is congruent to minus 1 mod p, and if f of p minus 1 is bigger than or equal to p, then it's also congruent to 0 mod p, but that's going to give us a contradiction. But what do we contradict? We contradict this assumption right here, which tells us that we in fact have f of p minus 1 is less than or equal to p minus 1. Really strictly less than p, but since we're working over the natural numbers here, we can say less than or equal to p minus 1. So let's go ahead and write that up here. So we've got f of p minus 1 is less than or equal to p minus 1, and that's for every prime. But then this purple box rule for n equals p minus 1 gives us p minus 1 is less than or equal to f of p minus 1. So mashing these two together, it tells us that for any prime, f of p minus 1 is equal to p minus 1. So that's actually a nice property to have as well. Okay, so let's go ahead and take that property and see if we can take it home. So now we're in a pretty good spot. We've got f of 1 equals 1, and for all primes, we have f of p minus 1 equals p minus 1. So now we're ready to work with those two conditions along with our original divisibility condition to go towards the end. So let's look at our original divisibility condition where m equals m. So in other words, m is free to be any natural number, and n equals p minus 1, where that is free to be any prime. Okay, so our original condition in this setup looks like p minus 1 factorial plus f of m factorial divides, so that's going to be f of p minus 1, but we know that that's p minus 1. So that's p minus 1 factorial plus f of m factorial. Good. So again, our original condition gives us this right here with these two cases. But now I'm also going to use like the fact that p minus 1 factorial plus f of m factorial divides itself. So in other words, p minus 1 factorial plus f of m factorial. Good. So now what we've got is p minus 1 factorial plus f of m factorial divides this thing, which I'll underline in orange, and itself, which I'll underline in purple. So as long as that difference is not 0, we know that it divides the difference. So I'll just like leave that text off, but I'll say it out loud again. So as long as that difference of the orange and the purple is not 0, this object right here, p minus 1 factorial plus f of m factorial, must divide that difference. So let's see what that gives us. So we've got p minus 1 factorial plus f of m factorial must divide, so it's going to be orange minus purple. But notice that orange minus purple is going to cancel out the p minus 1 factorial, and we've got f of m factorial minus f of m factorial, like that. But now there are infinitely many primes, so that's a fact. So that means that there are infinitely many things that divide f of m factorial minus f of m factorial. So let's go ahead and write that down. So f of m factorial minus f of m factorial has infinitely many divisors. But then recall from our third hint, which we proved really quickly, was that the only thing with infinitely many divisors was 0. So in other words, f of m factorial minus f of m factorial is equal to 0, and thus f of m factorial equals f of m factorial. And notice we had m up here was free, so that means that is true for all natural numbers m. So that's another nice property that we have. Okay, so I think we need one more chalkboard and we've got it. Let's recall we know f of 1 is 1, f of p minus 1 is p minus 1 for all primes p, and for all natural numbers we know f of m factorial equals f of m factorial. Okay, so now what I want to do is take m to be equal to p minus 1, where this is any prime. Again, we're going to use the fact that there are infinitely many primes, and we're going to let n be free. So in other words, that n is like any fixed natural number. So let's see what we get for that. We're going to have n factorial plus, so it's going to be f of p minus 1, but we know f of p minus 1 is p minus 1, so that's going to be p minus 1 factorial. That's going to divide f of n factorial plus, now we know that this guy right here can now be written as f of m factorial, but then since m is p minus 1, we know that f of p minus 1 is p minus 1, so that guy is is p minus 1 factorial. Okay, now we're going to use the same trick that we did before, which was now this guy must divide itself. So we have n factorial plus p minus 1 factorial must divide itself. So n factorial plus p minus 1 factorial. Now since n factorial plus p minus 1 factorial divides this and itself, it's going to divide that difference. So let's go ahead and write that difference down. So we have n factorial plus p minus 1 factorial divides f of n factorial minus n factorial. So let's see what we've got. We've got f of n factorial minus n factorial is divisible by this, but this divisibility holds for all primes p. But we know there are infinitely many primes, which tells us that this thing over here has infinitely many divisors. All of the primes are its divisors. But from that third hint on the very first board, we know that anything that's infinitely divisible, in other words, divisible by infinitely many things, has to be equal to 0. So here we have f of n factorial minus n factorial equals 0. In other words, f of n factorial equals n factorial. But if f of n factorial equals n factorial, then that means that f of n equals n. And that means that the only function that satisfies this setup is just the identity function f of n equals n. And that's a good place to stop.